myself Archana Sharma and I am here to deliver my lecture on the topic physical stability of suspension. First of all, we are going to discuss the factors which are going to influence the settling of the solid particle. Then in this we are going to first discuss what is the Brownian movement. So, Brownian movement of particles prevents sedimentation. So, if the particles are of the size range of 1 micron, 2 micron, they exhibit Brownian movement. Okay. And these particles, they do not have the tendency to get settled. Okay. In general, particles are not in stage of Brownian movement in suspension due to large particle size and higher viscosity of the medium. Brownian movement can be observed if the size of the particle is about 2 to 5 micron. So, in case of suspension, particles are in bigger size. Okay. So, they do not exhibit Brownian movement, and for observing the Brownian movement, the particle size should be below the range of 2 to 5 micron. Now, theory of sedimentation. The rate of sedimentation of particles can be expressed by Stokes law using the following formula. Rate of sedimentation is equal to d square rho 1 minus rho 2 g upon 18 neta, where d is the diameter of the particles in centimeter, rho 1 is the density of the dispersed phase, rho 2 is the density of the dispersion medium, neta is the viscosity of the dispersion medium in poise, and g is the acceleration due to gravity. Then Stokes law is applicable in the following condition: for particle should be spherical and particle should settle freely and independently. So, Stokes law applicable in two cases: only if the particles are of a spherical size, and another is that the particle should freely settle. Then factors affecting the formulation of suspension. First is your particle size. If the particle size is reduced to half of its original size, the rate of the sedimentation decreases by a factor of 4. A smaller particle facilitate rapid adsorption. So, if we are going to reduce the particle size to half of its original size, then we are going to reduce the rate of sedimentation by 4 times. Okay. Then viscosity. The viscosity of the suspension should be optimum. It is inferred that the higher the viscosity, lower is the rate of sedimentation. So, the viscosity of the suspension should be minimum, should be optimum, that and if it is concluded, it is observed that if higher the viscosity, lower is the rate of sedimentation. Density. If the density of the medium is equal to the density of the solid, the rate of settling becomes 0. Therefore, there is need to decrease the density of the medium, so that the difference in densities will be minimum. The density of medium can be increased by including the ingredients such as polyvinyl pyrrolidine, sugars, sorbitol or dextrose, polyethylene glycols, glycerin, etc. So, if we look into this equation, okay, so rho 2 is the density of the dispersion medium. If the density of the dispersion medium is made equal to the density of the solid, okay, then the rate of settling or the sedimentation will become 0, and we can increase the density of the dispersion medium by incorporating agents such as PVP, polyvinyl pyrrolidine, sucrose, dextrose, etc. Then now we are going to discuss the physical stability of suspension. Okay. What do you mean by the stability? The stability of the system or any dosage form is defined as the time period during which the substance or the product maintain its integrity as it was at the time of manufacture. That is the stability. How long the product will maintain its integrity as it is at the time of manufacture. So, physical stability is defined as the condition in which the particles remains uniformly distributed throughout the dispersion without any sign of sedimentation. So, in case of suspension, the stability is defined as the time period during which the solid remains suspended throughout the system without getting settled. That time period is called as physical stability of suspension. The extent of sedimentation is quantitatively expressed by two factors, that is sedimentation volume and degree of flocculation. Sedimentation volume, it is defined as the ratio of ultimate volume of sediment to total volume of suspension when the sedimentation occur in standard condition. So, if we consider the suspension, okay, so this is a suspension, suppose it is 100 ml. So, this is your volume of suspension, and if the solid is settled, this is considered as volume of sediment. So, your sedimentation volume, it is generally represented with the letter F, and it is defined as the ratio of the ultimate volume of sediment with respect to the total volume of or the initial volume of suspension. We can also define, or instead of taking the volume, we can also consider the height, and it is defined as the ratio of ultimate height of sediment to the with respect to the initial height of the suspension. F can assume a value of 1 when there is no sedimentation. Vu is equal to V naught, which is desirable property for an ideal suspension. So, F, where the value of F can lie in the range of 0 to 1. Okay. So, if the value of F is 1, that is the case of ideal suspension, that is, in this case there is no sedimentation. That means, all the solids are uniformly dispersed in the medium. At this stage, Vu is equal to V naught. Okay, that is why F is equal to 1. This is the ideal case of suspension. Okay. F can assume 0 value when sedimentation is complete, that is Vu is equal to 0, indicating total instability. Hence, the F value is in between these limits 0 to 1. The higher the sedimentation volume, better is the physical stability. So, the high value of sedimentation volume represents the better physical stability of the system. This can be observed, or this can be studied by performing a experiment. What we do? We take a series of suspension, and we prepare a series of suspension by using a different suspending agent or by varying the concentration of the same suspending agent. A series of suspension can be prepared using different suspending agent or varying concentration of same suspending agent. So, what we do? We take we make a series of suspension, okay, either by choosing the same suspending agent of different concentration or by choosing a different suspending agents. Then these formulations are transferred into 100 ml measuring cylinder. At different time interval, the sedimentation level in ml is measured. A plot is drawn by taking time on x axis and Vu by V naught, that is sedimentation volume, on y axis. At 0 time, this ratio is equal to 1 as Vu is equal to V naught. As the time elapses, the sedimentation level decreases, then the curve moves downward to the right of time axis and goes on. So, what we do? We make a suspension in a 100 ml, we can make a 100 ml suspension, and what we do? Then we add a suspending agent and we kept for the leave the suspension for some time to get settled at the 0 time interval. Okay. At 0 time interval, what will we what we observe, that Vu is equal to V naught. Okay? That means the value of sedimentation is 1. So, if we plot a graph in between the sedimentation volume versus time by taking time on the x axis and sedimentation volume on y axis. So, at 0 time interval what we observe, that there is no sedimentation take place. Okay, that means the particles are uniformly distributed in the system, but after some time what will happen, the particle, the solid particle, they start getting settled. Okay. So, now what we observe, that in the graph now the sedimentation volume will start decreasing as the rate of sedimentation increases. Okay. Then again after some time what will happen, all the solid get settled. Okay. So, at this stage what will happen, after some time the F value remains more or less constant. This is indicated by the parallel lines to the x axis. So, after some times what will happen, when all the solid particles get settled in all the 3E suspension, the F value becomes more or less constant. Okay. So, from this graph what we conclude, the time period, how long or at which concentration or which suspending agent imparts greater stability. Okay. How long the suspending agent prevents the settling. Okay. That suspending agent or that concentration of suspending agent is considered to be ideal for making the suspension. So, from the curve we can, a comparison of such curves permits the selection of better suspension. This method can be used to select better suspension, identify a suitable suspending agent or a optimum concentration of suspending agent. Next parameter is degree of flocculation. It is denoted by the beta. Okay. So, beta is equal to F by F alpha. So, it is defined as the ratio of sedimentation volume of flocculated suspension with respect to the sedimentation volume of deflocculated system. We can also define that it is the ultimate sediment volume of flocculated flocculated system with respect to the ultimate sediment volume of deflocculated system. If F is equal to F alpha, that is the sedimentation volume of flocculated suspension is equal to the sedimentation volume of deflocculated suspension, then the value of beta is 1. Okay. And if the value is nearer to 1, the suspension does not present a flocculated suspension. That means, the suspension is deflocculated suspension. It indicates that the system under study is deflocculated. The higher the value of beta, the greater will be the physical stability. Okay. So, for flocculated suspension, the value of the beta should be more than 1. The next another parameter is redispersibility. Evaluation of redispersibility of sediment is also important. The suspension may be placed in a 100 ml graduated cylinder. After storage and sedimentation, the cylinder is rotated through 360 degree at 20 rpm. Then end point is taken with when the base of the cylinder is clear of sediment, including the uniformity of suspended drug particle. The time required or number of revolutions are noted. The shorter the time or lower the number of revolution, the greater or faster the redispersibility. Okay. So, in case of redispersibility, what is redispersibility? When the particles of the suspension they get settled, then these particles need to redisperse in the system. So, if the particle they are if it can be redispersed, okay, then by applying the force, then this redispersion of the particle in the system is called as redispersibility of the suspension. So, what we take? We prepare a suspension, okay, in a 100 ml. We prepare a 100 ml cylinder, 100 ml suspension. Then what will happen? We kept for a storage. Okay. Then after storage, what we do? We rotate this suspension at 360 or 20 revolutions. Okay. We rotate this suspension at 360 degree at 20 rpm. Okay. And the time taken, okay, the time taken by the particle to get redispersed throughout the system, that time is noted down. Okay. So, the time, the shorter the time or lower the number of revolution, the greater or the faster is the redispersibility. So, how much time taken by the particle to get uniformly distributed or how much time taken by the particle to redisperse in the system, that time is taken, is noted down, and smaller if lesser time taken by the system, more is the physical stability of the system. In suspension, now we will discuss about the rheologic properties of suspension. Rheology of suspension. In suspension, the flow properties have profound influence in the manufacture during the storage and administration of drug. The flow properties such as pseudoplastic and thixotropic, that is gel, sol, gel behavior, are important for physical stability. During storage, the suspension exhibit gel-like structure and lowers the rate of settling. On moderate shaking, the product assume sol-like behavior which permits pouring of the product from the bottle. So, in suspension, rheology also plays an important role because it undergoes the transformation during the storage, that is from gel, sol, gel transformation. Okay. So, during the storage, the suspension exhibit in the form of gel, while in the form of gel to prevent the rate of settling of the solid particles, and on giving a moderate shake or a moderate force, the system transform it into the form of the system transform it into the state of gel to the solution. Okay. So, that it can be easily pourable from the container. And this behavior is observed by performing the experimental method. The experimental method involves the study of system from lower to high shear rate. Example, bentonite, V-gum, carboxymethyl cellulose. So, we study the rheologic property or the rheologic behavior of the suspension by using bentonite, V-gum, carboxymethyl cellulose, and in the system we give a lower to the high rate of shear. The resultant hysteresis loop of thixotropic curve are compared with those of the standard product. Then we compare the hysteresis loop of these three systems. So, we will compare the hysteresis loop of these three thixotropic curves with the standard one. The hysteresis loop of bentonite is quite marked. V-gum also shows considerable thixotropy. So, here is the hysteresis, here is the graph, okay, between the shearing stress and the RPM. Okay. So, here we can see this is the hysteresis loop for the bentonite, and this is the hysteresis loop for the V-gum, and this is the hysteresis loop for the carboxymethyl cellulose and bentonite. Okay. So, when bentonite and carboxymethyl cellulose dispersion are mixed, the resulting curve shows both pseudoplastic and thixotropic characteristics. Such a combination should produce an excellent suspending agent. So, what from this hysteresis from this diagram, if we compare the hysteresis loop of the 3, then this hysteresis loop of the combination of CMC and bentonite sorry, is hysteresis loop of CMC and bentonite is better as compared with the hysteresis loop of the individual bentonite and V-gum. So, the combination of bentonite and the carboxymethyl cellulose gives a good produce a good suspending agent, produce a good suspension. The consistency of suspension are evaluated using rotational viscometer. Brookfield viscometer mounted, so we can study the rheologic properties of the suspension by using a rotational viscometer. For the suspension we can use Brookfield viscometer. This is your Brookfield viscometer. Brookfield viscometer mounted on helipath stand with T spindle with may be ideal to study the behavior of settling. Okay. So, this is your T spindle which is mounted on the helipath stand. The T bar rotates and changes its position continuously. At the same time, it also descends slowly into the suspension. So, what will happen in the suspension? See, this is your suspension, this is your T shaped spindle. This spindle, it continuously rotates within the suspension, okay, and simultaneously it slowly descends into the suspension also. The part traced by the spindle is helix. The dial reading indicates the magnitudes of resistance. Okay. Since the T bar continuously encounters the undisturbed layer, the result indicates how the particles are settling with respect to the time. So, as the T bar, as this spindle rotates, it all the time encounters the undisturbed layers of the solid. As a result, it indicates the settling of the particle with respect to the time. As the T bar continuously descends newer layer of suspension, these techniques provide information about the level at which the flux network is greater due to aggregation. The effect of aging and storage can also be evaluated by using this method. Thank you.